Hi guys, in complex analysis volume 2 lecture series up to the last lecture I started just your calculus of residue. Calculus of residue. This is the topic I started on last lecture, in which I told you up to the last lecture. First thing I discussed zeros, and I told you zeros means if we put fz equal to 0, then solution of z, values of z are called zeros of the function. Second thing I discussed about singularity of function. Singularity of function, or you can say a singular point of the function, in which I told you if any point, a point z equal to a, at which fz is not analytic, then this is a single point or singularity. And on the last lecture, I told you this singularity is of two types. One is isolated and other is non-isolated. That is depending upon the neighborhood of point A. If z equal to A is a singularity and its neighborhood no other singular point, means function is not analytic at point A, but it is analytic in the neighborhood of point A, then this is called isolated singularity, otherwise non-isolated. Non-isolated means if we take point A and this is a singular point, and if other singular points also exist in this circle, in this small circle, in the neighborhood of point A, then we say that here z equal to A is a non-isolated singularity. This, up to this lecture I discussed, up to this point I discussed on the last lecture, and now I am going to start further types of the singularities, as I told you. Because non-isolated singularity is not a part of our curriculum, but in isolated singularity, if further we study, then I see that there are various types of the singularities like poles, removable singularity, and essential singularity. Means there are only three types of the singularity. In case of isolated singularity, we have some special types of singularity. Other types of singularity, in which basically there are three types of singularities. Actually, there are basically three types of singularity. One is poles, second is removable singularity, and third is essential singularity. Essential singularity is also called isolated essential singularity, because all of the kinds of isolated singularity. Means isolated singularity, I told you, okay, a point at which function is not analytic, but there is a possibility that function may be analytic in the neighborhood of that point. That is the isolated singularity. And in all three types of singularity, we can define very easily by the help of Lorentz theorem. Because Lorentz theorem, by Lorentz theorem, we know that fz equal to sigma an z minus a to power n equal to 1 to infinity plus sigma n equal to 0 to infinity, n equal to 1 to infinity bn z minus a to power minus n. This is the Lorentz theorem. I told you, here we take a ring shape annular region where point z equal to is the center and z is this point, then function is analytic in this ring shape region, then we can expand the function in the help of Lorentz as some containing some positive power of z minus a and some negative power of z minus a, and that is infinite series. And in this series, I told you if this part is called principal part of Lorentz theorem, and that is very important part. So, and with the help of this part, we can define all three types of the singularity. How is defined? It will depend upon Bn, our principal part. This principal part is what is at point A, right? And there are three possibilities. By principal part, we can define singularity, and so for principal part of equation 1, there arises three possibilities. What are the possibilities? One, maybe the principal part has finite term. Second, principal part has no term. Third, principal part has infinite. And on basis of these three possibilities, we can define these types of the singularity. Means we can define poles, removable singularity, and essentials. If we take first possibility, that if principal part of Lorentz theorem has a finite number of terms, right? Finite numbers of terms. If we take this one, that means Bn is 0 for n is greater than n. That means n is any number. Then principal part finite number of terms, and then is in this case z equal to a is called simply a pole of order n. Means only this, in this expansion, this part contains only finite terms. And after that means if we expand this, that will be expanded from n equal to 1 to m. That means this term is b1 upon z minus a, b2 upon z minus a square, b3 upon z minus a cube up to bm upon z minus m. And after that, all terms are vanishing, so it contains finite terms. And here you see that z equal to a is a singular point, and this is called a pole of order m. This is definition of pole. Second thing, if principal part of Lorentz theorem has no term, that means Bn is 0 for all n. This terms completely, this expression, this portion is vanishing. No term, only we have this term. And you see here, now here singularity is saying z equal to is a singular point, but in this singular z equal to is not a singular point. So function becomes analytic, and in this case z equal to a is called removable singularity of fz. That is the result of second possibility when the principal part of Lorentz theorem has no term. Now, third possibility is called. Third possibility, if principal part of Lorentz theorem has infinite number of terms. That means now Bn is non-zero for any value of n. That means now in equation 1, your second term is containing infinite number of terms, right? In this case, z equal to a is called an essential singularity of fz. These are the basic differences. You can say these are the definitions of poles: removable singularity, essential singularity, or you can say these are the basic differences between all of three, and I defined with the help of Lorentz theorem. Means all the types of the series, all the types of that is depending upon the principal part of this. Here, in first case, I told you if Bn is 0 for some greater value of m, means that is non-zero up to them and then 0, then this is a pole of m. If m equal to 1, then this is called simple pole. That means simple pole means pole of order 1, right? Otherwise, pole of, if there is m is 2, then pole of order 2. If m is 3, then pole of order 3. M is 4, then pole of order 4, and so on. If Bn is 0 for every n, that means principal part is completely vanishing. Now, naturally, singularity has been removed, and so z equal to a is called removable singularity. Third case, if Bn is non-zero, and that means principal part is containing infinite number of terms, then this is called essential singularity. Now, first I will take an example, and example of both of this. Simple example, numerical example, by which you can better understand what are the basic differences and what are the basic concepts of the singularities, right? And then I will proceed further how you can define these singularities, these type of singularities with the help of calculus, and because this chapter is namely calculus of residue, and then I will define what is residue at whom, right? If we take three simple examples based on, right, in which we can say that if we take fz equal to ez upon z minus 2 whole cube. Simply, you see here is z equal to 2 is a pole of order 3. Simply, right? And second, if you take example fz equal to sine of 1 upon z, sine of 1 upon z. So here you see that z equal to 0 is a singular point, because this fz tending to infinity and limit does not exist. A singular point is an essential singularity, right? Because if you expand this by sine 3, then 1 by z minus 1 by factorial 3z cube plus 1 upon factorial 5z5 and so on. So here we see that z equal to 0 power containing infinite of terms. As I told you in principal part, if principal part contains infinite number of terms, then z equal to a is called essential singularity. Similar here. And third example of removable singularity you can take as if we have fz equal to sine z minus 1 upon z minus 1. So here we see that z equal to 1 is a removable singularity. Because if you expand this again by sine series, so this is z minus 1, this is z minus cube, this is minus z minus 1 cube upon factorial 3, z minus 2 power 5 upon factorial 5 minus 1. If you cancel this, then 1, this is z minus 1 is cancelled out, second term becomes z minus 1 upon factorial 1 power is cancelled out, z minus 1 to power 4 upon factorial 4 and so on. So here you see that in this function, we see that z equal to 1 is a singular point. But if we expand this, then this singular point has been removed, because in this series, if you see that z equal to 1 is not a singular point. If we put z equal to 1 here, we get 1 that is defined, that exists, and so it is a removable singularity. So in this in our syllabus, 3 types of the singularities: poles, removable singularity, and essential singularity. And by this concept, we can this, and also we have also we can define all 3 types of similarity in other method. You can say also there are various methods to find the similarity, or you can detect the similarity if given function. Another method that is very simple method by the help of calculus. Various methods to check types of similarity. If by calculus we see that, so there are very interesting methods. There are very interesting methods by which we can check singular point or similarity exists or not. If it exists, so what is the type of the similarity? Means if you take a function, fz is any function, and z equal to a is a singular point of fz, right? Naturally isolated singular point. Then here we have to check, we have to detect what is the type of this singular point, what is the type of this similarity. It is pole, it is removable singularity, or it is essential singularity. That is a very simple method of calculus. That is the method of limit. Only you have to find the limits. What is if we calculate limit of this function as z tending to a, and you know that method to find the limit. So we calculate the limit of this function, right, at point A. Then there may be 3 possibilities. That means there may be 3 results, 3 answers of this limit. First, limit exists. Second, limit value of limit tends to infinity. Third, limit does not exist. These 3 possibilities are only here occur, nothing else. So if limit exists, then it is a pole. Limit exists, then it is a removable singularity. If limit tending to infinity, not finite, means infinite, then it is. And if limit does not exist, then it is an essential singularity. That is very simple. Means if limit exists means its value is finite. Then we say that this is removable singularity. Second possibility, if this limit is tending to infinity, its value is infinity, then this is a pole. Third possibility, if this limit does not exist, then this is essential singularity. Right? These 3 possibilities, this is another method by which we can check, we can detect what is the type of the given singularity. Means if given function is given point, you know the point, singular point, what is singular point. So simply we calculate the limit of the function at that given point. If limit exists, then it is removable singularity. If limit is infinite, tending to infinity, then it is pole. If limit does not exist, then it is essential limit. For example, if we take fz equal to, take first example, z square minus a square upon z minus a. So here you see that z equal to a is a singular point. If we calculate the limit z tending to a of fz here, then we get limit z tending to a. Factorize this by the process of finding calculation of limit z minus a, z minus is cancel out, that is 2a. That means limit exists. That means z equal to a is a removable singularity. This is the first possibility. Function is given, you find the limit at point A. So you see that limit, value of limit is 2a, that means limit exists, value is finite. So z equal to a is a singular point here, but it is removable singularity. Similarly, second case, you take function fz equal to z square plus a square upon z minus a. If here you find the limit, you calculate the limit z into f of fz, then limit z tending to a of this function z square plus a square z minus a, it becomes infinity, right? And then that means limit again infinite. So here we can say that z equal to a is a pole of fz, and naturally here is a factor of power 1, so it is a simple pole. Third case, if we take example of fz equal to fz equal to e to power 1 upon z minus a. Now calculate limit of this function as z approaching to a, that is limit z tending to a of e to power z minus a. If we expand this in form of exponential series, then we get, you know that e to power x is series equal to x, 1 plus x square by 2 plus x3 and factorial and so on. This is 1 upon z minus a plus 1 upon factorial 2 z minus a square 1 upon 3 z minus a whole cube plus 1. This one, right? If we calculate the value, this limit does not exist because its value is infinity into infinity, that is does not exist. And limit does not exist means in here this implies that z equal to a is an essential singularity, right? That is the another method, that is very effective method, and you see that that is very shortcut method to find the types of the singularities, right? And that is the very simple method. If you have given a function and you know what is the point of singular point and you have to check what is the type of singularity, simply calculate the limit of given function at point A. If limit exists means value defined, well defined and finite, then we say that this is a pole. If limit tends to infinity, then we say that if limit exists and value finite, then we say that this is the removable singularity. If limit tends to infinity, then we say that that is a pole. If limit does not exist, then we say that that is the essential singularity. That means that is very easy method to find the types of limit, because in one calculation you know that what is the type of limit. And then come to the main topic. Your heading is the residue. That is the calculus of residue, and for that we define here singularities, and that is the main topic. That is the residue. Residue at pole. What is the residue at pole? First, I define here. I take its basic definition. What is the basic definition? If z equal to a is a pole of a function fz, right? Pole of a function of order m. Suppose and C1 be a circle with center at A and radius small r, right? And which does not contain any other singular point. Then we see that Fz is analytic in 0 is less than z minus a is less than small r is less than capital R. Means the ring shape region, this is the region. This is point A, this is circle C1 with radius R, this is main point C and function is defined, this is small r and this is capital R. Function is analytic, function is analytic in this region and so on. Right? Then Fz can be, and so Fz can be expanded as by Lorentz theorem. By Lorentz theorem, that is Fz equal to sigma n equal to 1 to infinity a n z minus e to power n plus sigma n equal to 1 to infinity b n z minus e to power minus n. That is the principal part. Right? By this theorem, by Lorentz theorem. Then you know that here an is 1 upon pi I integral c fz upon z minus a whole power n plus 1 dz, and you know that bn is equal to 1 upon 2 pi I integral c1 fz upon z minus a to power minus n plus 1 dz. Right? In the principal part. So here we see that this is varies from pole. So with this here, this is varies by bn is 0 for n is greater than m and so on because of singular point. So here, if for n equal to 1, b1 we have b1 is equal to 2 pi I integral c1 fz and dz. Right? Then residue is defined on basis of this. Then we say that this b1 is called residue of pole z equal to a at then this b1 is called residue of fz at pole z equal to a. This is called pole of residue of this and is denoted as and denoted by res z equal to a equal to b. This is the basic definition. Actually, this coefficient of Lorentz theorem in principal part is called residue, and naturally this is an integral 1 upon 2 pi I integral c1 fz dz. Actually, this is the basic definition of residue. Means in if we conclude this in very simple words, we can say if z equal to a is a pole of order m, then the coefficient of 1 upon coefficient b1 in the principal part of Lorentz theorem is called residue. And naturally, by formula in Lorentz theorem, b1 is defined as 1 upon 2 pi I integral c1 fz dz. This is the basic definition of residue at pole. In next lecture, I will discuss what is this is the basic definition of residue. In next lecture, I will discuss some other concepts based on the residue, and then I will tell you what are the methods to find the residue of pole, because you know that we have two types of the poles. One is simple pole. Simple pole means that there is a factor of degree 1. linear factor corresponding to you will get the value at which function is not analytic. And another pole is the pole of any order. From here, if we take m, if we have quadratic factor z minus 2, z minus a whole square, then that is a pole of order 2. If we have cubic factor z minus a whole cube, then we get pole of order 3 and so on. Okay, in next lecture I will discuss what are the other concepts of the residue and then what are the numerical methods to find the residue, because in calculus of residue main the objective main aim is this, that we have to solve the other type of the complex integral by the help of residues, and residue will depending upon the poles, and pole is a type of singularity. So here we are studying about singularity because we have to solve some other type of the complex integral. Okay, thank you.